Hello and welcome back to CMIS468. Remember we left off without getting into TCP/IP last time because the energy level in the room was low, my energy was low, so we can finish this up this way. I apologize for the lack of an attractive background. We're deep in my dungeon here, so here we go. TCP/IP, the most popular networking standard in the world by far. Great test question there. What you need to know about TCP/IP is that everybody uses it. There's a slide here. The book says that most corporate internets, that is to say corporate networks, use TCP/IP. Actually, it says many. I scratched that out and put most. I would say 99% of all companies use TCP/IP. It's huge. There used to be other standards that bit the dust back in the day, but TCP is it. It's called the TCP/IP standard because the two major protocols are the IP protocol here at layer 3 and the TCP protocol at layer 4. But as you can see, there are other protocols at other layers. At layer 5, HTTP is part of the TCP/IP standard. UDP is part of the TCP/IP standard. There are many protocols. So TCP/IP is a suite of protocols. There are many. If you Google TCP/IP, you'll see what I mean. Or just look at the wiki. There are a ton of them. There are only a few that we're going to get into in this class, just basically the most important ones. At layer 3, again, remember everything in red is test worthy. So IP is a layer 3 protocol that's at the network layer or internet layer, depending on your terminology. At this layer, messages that pass at layer 3 are called packets specifically. If you looked at the video that I assigned from last time of the guy walking through the layers, messages are called different things at different layers. So at layer 4 they're called segments, at layer 3 they're called packets, layer 2 moves frames around, and layer 1 is just the raw data transmission. And the important thing about layer 3 with IP addressing, every single host on the network has to have a unique IP address. It is theoretically possible to duplicate an IP address on a network. You don't want to do that. It's a bad thing because people get pop-up messages saying you have a duplicate IP address on the network, and if that pops up on a server, bad news, very bad. Some other standards within the TCP/IP protocol stack. TCP is the big one at layer 4. This is what chops up messages into segments. So remember I said that really big messages, just like a huge Subway sandwich, have to be chopped up to get sent across the network. TCP is the protocol at layer 4 that does that segmenting. It also does some error correction and some other things, as we'll see in future chapters. UDP is also at layer 4, and these messages are called datagrams. If you want to be a geek snob, you can remember that they're called datagrams instead of segments, but segments is the word I want you to really key on here. UDP packets are really small, like ping uses UDP, SNMP uses UDP. There's some others that we'll talk about. Also within the TCP/IP stack of protocols, there's several called supervisory protocols. DHCP is one, NAT is another, DNS is another. These are all critically important. So any network engineer has to know these inside and out. DHCP is the protocol that automatically assigns an IP address to every single host on a network if you have it turned on, and most corporate networks have it turned on. There is an argument to turn this off, even though it saves a lot of trouble, but it is something of a security hole in that any vendor, any salesperson, any guest on your network who can plug in, has physical access to plug into your network, will automatically get assigned a DHCP address. Most people leave it turned on because it's too much trouble to assign static or fixed IP addresses to everything. We'll set fixed IP addresses for servers, for printers, for wireless access points, things that don't change. But for PCs and laptops, you by default want to use DHCP. So it assigns, the server assigns it to the PC as soon as the PC boots up. So the act of booting up, one of the very first things the operating system does, use Windows as an example, as Windows is booting up, it'll send out a request for a valid IP address using the DHCP protocol. It's a dynamic protocol because it's temporary. It has a specific lease, and you assign the lease time, whether it's 3 days or 2 weeks, and that IP address, if you no longer need it, will expire. There are reasons for this. DHCP is a great example of a client-server protocol. The client requests a service and the server responds. In this case, we're talking about old-fashioned 32-bit IP addresses. And notice that the DHCP server gives you, it actually gives you five very important things. It'll give you your IP address, it'll give you your subnet mask, which is also important, but that's I think a later chapter. It'll give you your default gateway, also known as the IP address of your router. It'll give you your lease time, like I said, either 3 days or 10 days or 2 weeks, whatever the network administrator sets for it to expire. And the fifth item is it'll give you the address of your DNS server, your closest DNS server. We're going to talk about DNS next. But first I want to talk about how, this is probably how your network at home is configured. You've got maybe a cable modem with Charter. You've got your cute little Linksys or D-Link or Belkin box that's everything. It's a router, it's a switch, it's a wireless access point, it's a firewall, it's also a DHCP server, so you don't need a separate DHCP server because this box is acting as your server. And your printer, your laptop, everything's going to pick up a DHCP address this way. Similar setup on a corporate network, but obviously much, much larger, and you need a dedicated DHCP server because there's so much traffic. Usually the DHCP server is set up on your Active Directory box for convenience. And yeah, so in order to explain the next supervisory protocol, I want to talk about a problem. For example, Charter will only give you one valid public IP address, one, but you have many addresses on your local network. So the problem is, how do you get many addresses to connect if every device needs a unique IP address, but you only have one public IP address? And no need to draw it out because the answer is on the next slide. It's NAT. The Network Address Translation Tool is the protocol. Test question. This is a test question. The Network Address Translation Protocol is the protocol that lets you have many devices on your private network sharing one public IP address. So, for example, your external address might be something like 60.47.243.112, but inside your network it's going to translate that to 192.168.0.6 or whatever internal scheme you're using on your network. So it translates an internal address to an external address. It's for sharing multiple IP addresses. It's also a security feature, as we'll see. So switching to the third supervisory protocol I want to talk about today is DNS, the domain name system. You can do an entire semester on just the ins and outs of DNS because it can get pretty complex. But at a superficial level, it resolves IP addresses to names. And the only reason we even need DNS is because we're human beings, we're not computers. Computers can use IP addresses all day long happily. They don't need to resolve return name. But human beings just need DNS names, so it's easier to remember www.google.com. So the way DNS works is, this is another example of a client-server app, or network application architecture, client-server architecture. The host has to make a request of the server, but kind of a pop quiz question: how does your box know where the DNS server is in order to make the request? How does it know? I did answer this question already, but just to see if you're paying attention, right? The answer is, yeah, DHCP. Remember I said DHCP, when you boot up, tells you five things, and the fifth one was the location of your DNS server. So that's good to know. It's good to know for troubleshooting. It's good to know for a variety of reasons. So the DNS server is going to resolve, your local DNS server is going to resolve the name if it knows where it is. If it does not know, and it resolves it and sends it back. Let's see if the next slide shows. yeah, and this is where I wish I had a whiteboard, but the local DNS server, if it can't resolve it, it's going to escalate the issue to an external DNS server, something outside of its network, possibly a root DNS server. We'll talk about root DNS servers later on in the course. But the main idea here is that if your local DNS server isn't able to resolve the address, it's going to ask another DNS server on the internet, and that external DNS server is going to pass the information back to your local DNS server. It's never going to communicate directly with the PC. So it's going to go from one step to the next step to the next step in a hierarchy. So this idea of DNS being in a hierarchy is critically important. So once it's resolved, and by resolved you can think of translated the IP address to the name. For as long as that session is up, it doesn't have to keep looking it up. It knows for the duration of that session how to resolve it. So in that sense, it's somewhat efficient. Another pop quiz. So DHCP and DNS both deal with IP addresses, and it's easy for students to get confused on this because, well, they both start with D, right? And they both have to do with IP addresses. But a DHCP sends you the address of your client PC. DNS sends you the address of the PC that you want to get to, the server that you want to get to. And just to show you what this looks like, you can configure all this. So by default, I said DHCP is enabled automatically. This is kind of an old screenshot, probably Windows XP. Oh my God, I'm so embarrassed. But it looks very, very similar up through Windows 10. By default, this obtain an IP address automatically is checked, and that means you're using DHCP. But if you wanted to assign an address, you can, but you also have to get it with the mask and the default gateway, topic for a later date. You can also tell it to use a specific DNS server. This can be handy for troubleshooting DNS issues. So the same way, this is on the client side where you configure it. On the server side, this is an example of what the DHCP configuration looks like on the server. How does it know what IP addresses to assign? Well, because you give it a range, and in DHCP it's called a scope, the range of addresses for it to assign. And then here's that lease I was talking about, to decide how long you want to give out addresses. This is an example of what the DNS server piece looks like on the server side. So it's handy. This is coming back to ping, really the first homework assignment. Ping is so important because ping is that tool that lets you ping either an IP address or a domain name. And so this helps you troubleshoot if DNS is working or not. I said that there's some pros and cons to static IP addressing. You definitely want to assign static IPs for your servers. You've never set them up to actually use a DHCP assigned address, just because you don't want your servers wandering around the network with different IPs. You want those fixed for a variety of reasons. So I'll end with this thought that DHCP and DNS, they both start with D, but they do two different things. But they're both databases. When I talk about translating from one thing to another, if you want to think of it, and it is, technically it is a database. DHCP links MAC addresses, your physical address of your network card. It maps it to an IP address. DNS is another database that maps an IP address to a domain name. They're both mapping two different things. And both of these services, DHCP and DNS, will usually run on your AD box, your Active Directory box, your LDAP box in a Linux environment. If you have an old school environment, your boss might still call this a domain controller, but we haven't called it a domain controller since Windows NT back in the day. So that's a brief recap, but I would definitely go back and make sure you're comfortable with DHCP and DNS, one of the more important things in this chapter, but we'll do another pass through later on in the semester. So as usual, feel free to contact me if you have any questions at all about the content of Chapter 1, because, well, it just accelerates from here. So good luck, and I'll see you Tuesday. Thanks.